Hello students. Today we will discuss about the second application of Gauss theorem. Applications of Gauss theorem. Second application is electric field intensity due to a charged spherical cell. It means due to a hollow conductor. Let we have a hollow conductor of radius r. Property of hollow conductor is if we give some charge to it, then all the charge will distribute uniformly over its surface. This is the property of hollow conductor. Means Q inside it will be 0. We have to calculate electric field intensity due to this charged conductor at 3 points. One is outside, second is on the surface, and third is inside. So we have, let R be the radius of a hollow conductor having plus Q charge uniformly distributed over its surface. If sigma be the surface charge density, then sigma is equals to dq by ds, and from this equation we can get dq, sigma into ds. Okay, we have to calculate electric field intensity at a point P at distance r, small r, from center of cell or spherical, hollow spherical conductor, right? Case 1. If r is greater than r, point P lie outside the cell. Using Gauss theorem, we will be having at this point P at distance r. Okay, suppose we are taking a Gaussian surface along it. This is radius r, and this would be the Gaussian surface, and this is the normal at this point where we have to calculate electric field intensity. So E dot ds for a closed surface is always equals to 1 by epsilon naught into q, and this gives us E into integration of ds is equals to 1 by epsilon naught into q. E into, what is the integration of this surface area? That gives 4 pi r square into q. So E is equals to 1 by 4 pi epsilon naught into Q upon R square. This is the first case. So E is inversely proportional to square of the distance between center and that point. This was first case, and it is similar to that of charged charged solid sphere. Now case 2. For case 2, we have to choose that point on the surface. Now I am taking that point on the surface so that R equals to R. So this will be the Gaussian surface, spherical body itself. Case 2, when R is equals to R, point P lie on the surface. Okay. Since sigma is equals to dq by ds and dq is equals to sigma into ds, we can integrate this to get the value of q. So integration of dq is q, sigma is constant, and keep it as it is, integration of ds. Using Gauss theorem, E dot ds is equals to, for this we have normal in this direction, 1 by epsilon naught into q. So it become E ds cos 0, because normal and electric field lines are in same direction. So E into ds is equals to 1 by epsilon into q. E into ds, what is the value of q? Q is equals to sigma into ds. So ds to ds cancel, we will be having E is equals to 1 by epsilon into sigma, and on the surface that is maximum and constant and maximum. This was case 2. Case 3, when R is less than capital R, that is point P lie inside the cell. We know that inside the cell Q is 0. So if we put the value here, then we will get E also 0. Since Q is equals to 0 inside the cell, so E becomes 0. So these were the 3 cases, and conclusion is, from center to before the surface, before reaching the surface, electric field intensity will be 0, and when we reach over the surface, then it becomes maximum, and again when we go away from the surface, then it will follow this. In this regard, we can plot a graph it represents distance and it represents magnitude of E. From center to C2 before reaching to the surface, E becomes 0. As we reach on the surface, it becomes maximum at R equals to R, and after this it tends to 0. So this is the graph. Okay, now we have next application, that is electric field intensity due to a straight linear charged conductor. Third application, electric field intensity due to a linear charged conductor. Okay, so let us take a linear conductor having plus q charge uniformly distributed over the length. Because this time we are taking a linear conductor, so we will take linear charge density. Due to this linear conductor, the Gaussian surface will be cylindrical in shape. Why? Because electric field lines are in this direction as well as in this direction, so all around to the conductor. If we make a tangent of all the electric field lines, then it will give us one circle at that point, and similarly it gives the same circle at every point. Now if we draw a tangent to every circle, then we will get one cylinder. So what is the shape of the Gaussian surface? Cylindrical Gaussian surface. Okay, if the length of the conductor is L and if R is the radius of the Gaussian surface, cylindrical Gaussian surface, then we have to choose 3 points at least. One, this is the direction of normal. One is this normal, and second I am taking one point here, that is this normal. And electric field is always away from the linear charge conductor in a direction perpendicular to it. So for this we will be having we have 3 points, 1, 2 and 3, this one. Okay, these are the directions of normal of this cylindrical surface, cylindrical Gaussian surface. But the direction of electric field is this one or this one, means perpendicular to it, either this one or that one, right? So the direct angle between normal and electric field lines here is 90 degree. Similarly here it is also 90 degree, but in this case angle is 0 degree. Let a linear charged conductor is having linear charge density lambda. So lambda is equals to Q by L. So what is the value of Q? Lambda into L. Fine. Now take a point P, this is P, or you can take this one as P. Okay, take a point P at a distance R unit from the conductor, where we have to calculate electric field intensity using Gauss theorem. So So E dot ds is equals to 1 by epsilon into q. E into, that is electric flux. So that is electric flux. We have chosen 3 points, so we can take region because flux is equals to 1 by epsilon naught into q, and we have chosen 3 points, so we can write as E dot ds for a closed surface for part 1, E dot ds for 2, and E dot ds, sorry, E dot ds for 3, that is equals to 1 by epsilon into q. Here angle is 90 degree, so it will be 0, into as well angle is 90 degree, so it becomes 0, and in 3 angle is 0 degree, so it will be E into ds, that is equals to 1 by epsilon into q. So after this we can get E into ds is equals to 1 by epsilon into q. What is the surface area of a cylindrical part? That gives 2 pi r into L into equals to 1 by epsilon into q. What is the value of q? Lambda into L. L to L cancel, so E is equals to 1 by 2 pi epsilon naught into lambda upon r. From this relation we can say that E is inversely proportional to r, this one, radius of the Gaussian surface, and it is independent of length of the conductor. There is a graph for r versus E, so it will look like this. This was the second application. You can write one thing, E is equals to, multiply and divide by 2 both sides, 1 by 4 pi epsilon naught into 2 lambda by r, because this is our constant quantity. This was the third application. Now fourth application. Fourth application is electric field intensity due to a thin charged sheet. Electric field intensity due to a thin charged sheet. Okay, suppose we have a charged sheet of negligible thickness and having plus q charge uniformly distributed over its surface. If sigma is the surface charge density, then now let us assume one cylindrical imaginary Gaussian surface which penetrate this sheet. It is penetrating through this sheet. Okay, and the direction of electric field is due to this sheet. Suppose this is of negligible thickness, so one electric field line, if charge is uniformly distributed over this surface, then electric field line will be like this, perpendicularly in this direction and perpendicularly in this direction. Okay, so we will be having two sections of electric field lines. One is this and second is this, because it is having positive charge. So electric field line will be perpendicularly outward to the plane. So I am taking electric field lines here, this one E, and in this direction E, right? And we can take a normal of this surface. This is the normal N. Also this is another normal, and one point we can take here, normal, right? If sigma is the surface charge density of a thin sheet, then sigma is equals to dq by ds. We have 3 points, 1, 2 and 3. Electric flux due to this thin charged sheet is given by phi E is equals to 1 by epsilon naught into Q. And there is another term, E dot ds for first, E dot ds for second, and E dot ds for third. That gives us 1 by epsilon naught into Q. Here direction of electric field is this and also of normal, so angle will be 0. E ds cos 0 plus, in same way, E ds cos 0 because of this direction and that direction of E and N, plus, now here electric field line is in this direction but normal is in vertically upward direction, so E ds cos 90, that gives us 1 by epsilon naught into Q. So this is 1, this gives us 1 and this gives us 0, so it will become E into ds plus E into ds plus 0, 1 by epsilon into Q. It becomes 2 times of E into ds is equals to 1 by epsilon into Q. Now we have value of dq is equals to sigma into ds. If we integrate both sides, then we will get q is equals to sigma into integration of ds. So we can say equation number 1. From equation number 1 and 2, one and 2, 2 times of E into ds is equals to 1 by epsilon into what? Sigma into ds. So we can cancel ds. E becomes sigma over 2 epsilon naught. This will be the result due to a charged sheet of negligible thickness. If the sheet is having infinite thickness, then result will be E is equals to sigma over epsilon naught only. Okay. The last application of Gauss theorem. We have to calculate electric field intensity due to 2 parallel charged sheet, and we have to use this result only. Fifth application, electric field intensity due to 2 thin due to two parallel thin charged sheet. Here is the diagram. Suppose we have two charged sheet having sigma 1 and sigma 2 as surface charge density. Let plus q charge is uniformly distributed similarly here. Okay. With the help of previous application, we can say that there are some electric field lines in the direction perpendicular to the surface of this sheet, in this direction and in this direction. Okay, so electric field lines goes like this and in this direction as well. E1. Okay, electric field intensity due to first sheet. In similar manner, we will be having electric field intensity due to second sheet. E2. We have three sections, 1, 2 and 3. First, left side to the both sheets, second in between the two sheets, and third is right side to the parallel sheets. Because direction of E1 and E2 are in this part, we have right to left, left to right and right to left as well, and from left to right. So we will take a reference of E naught, that is external electric field. This is for reference only. So in E1 and E2, if any part is going from left to right, then we will take positive. If it is going from right to left, then we will take negative. Okay, this is the importance of external field. In section 1, net field is given by, so E in 1, that is given by minus E1 and minus E2, because both of them are moving from right to left. And what is the result for E? Sigma upon 2 epsilon naught, with the help of previous article. So what is the value of E1? That will be sigma 1 over 2 epsilon naught minus sigma 2 over 2 epsilon naught. We can take a common 1 by 2 epsilon naught with my negative sign, sigma 1 plus sigma 2. Equation number 1. Similarly, in section 2, this one, net field is given by E into, that will be E1 minus E2, sigma 1 by 2 epsilon naught minus sigma 2 by 2 epsilon naught. We can take a common 1 by 2 pi epsilon naught, sigma 1 minus sigma 2. Equation number 2. In section 3, E is given by E in third. Both of them will be positive. So sigma 1 by 2 epsilon naught plus sigma 2 by 2 epsilon naught. 1 by 2 epsilon naught is common, sigma 1 plus sigma 2. Equation number 3. We have 3 cases now. Now there is one special case, that is if sigma 1 is equals to plus sigma and sigma 2 is equals to minus sigma, means the another sheet is having equal but opposite charge on its surface, then E in 1, this portion, minus 1 by 2 epsilon naught into, that is sigma 1, that is sigma, minus sigma 2, that is minus sigma, minus minus plus. Yes, okay, this was the case, sigma 1 plus sigma 2, so plus minus minus, so it gives us 0. So there will be no electric field if both the sheets are having equal and opposite charge. In 2, now we are having 1 by 2 epsilon naught, sigma 1 is sigma and minus sigma 2 is minus sigma, so it gives 2 sigma upon 2 epsilon naught, so sigma upon epsilon naught. So electric field will exist in between the sheets. E in 3, 1 by 2 pi epsilon naught into sigma 1 plus, it becomes minus, that gives us 0. So only field will exist in between the sheets if they are having equal and opposite charges on their surface. So these were the applications of the Gauss theorem. Okay.